So momentum and Newton's second law. Well, if you remember, Newton's second law says what? The net force equals what? Mass times acceleration. What's the definition of acceleration? Isn't acceleration change in velocity over change in time? So if I put that into this equation, the net force equals mass times change in velocity over change in time. And what's mass times velocity? Isn't that linear momentum? So now we can say the net force equals change in momentum divided by time. Or change in time if you want to. Now what is change in momentum? Let's continue. Equals final momentum minus the initial momentum, which is what? Final momentum is mass times final velocity, mass times initial velocity. Now let's go back to that equation here. Can I rewrite this equation? I can say change in momentum is equal to the force, the net force times change in time. Cross multiply, that's over 1. If you cross multiply that, you end up with that equation. And since change in momentum is equal to this, and that's also equal to this, and there's the equation I'm trying to derive. Right here. Now, this value here, force times delta time, is actually called impulse. We use the letter I, it's a vector again, is equal to the force times delta t. So let's take an example and go through it and see. Maybe we'll do a home run here. Baseball. Let's give it some numbers. So a ball's traveling this way. Pitcher throws the ball to the batter, so I can't really throw it, I'll just put the bat there. That's the baseball bat. The ball's traveling this way. Baseball has a mass of what? We said roughly 150 grams, 145, 150, which is 0.145 or 150 kilogram, or kilogram, not grams. Let's pick a pitcher. Who is the pitcher going to be pitching today? Anyone has somebody in mind? Not? I use Chris Sale. He throws hard. The ball, or Kelly. The ball is coming this way at a speed of 115. Well, that's really fast, but 98 miles per hour. Okay. Now, the ball hits the bat and it's going to leave now. I don't want to jinx the Red Sox tonight. It's going to leave with the speed of 105 miles per hour. Usually the impact time is very short. The impact time between the ball and the bat, it's usually less than a tenth of a second. Way less than a tenth of a second. So this is the impact time, the time where the ball in contact with the bat, it's roughly, I don't know, 0.04 second. I'm just making that number up. When you see the bat hits the ball, actually, the ball comes in, and you can't see it in the naked eye, but if you slow the camera, you'll see actually that this will break. Let me take a different one, since that's broken. When the ball hits that bat there, you will see a dent like this in the ball. It wraps itself around it, then it will bounce back. It's like a spring loaded. That's what happened actually with the baseball. And you see a lot of home runs hitting these days, being hit. They go, why? Because the ball is juiced. More bouncy, like a Super Bowl almost, compared to the ones we had years ago. But the ball will go like this around the bat. Can you see it? I don't know if you can see it. It's like wrapped itself around, then it will go, because spring loaded. And it will go forward. That's why the speed leaving, plus the person swinging the bat, like Mookie Betts has phenomenal bat speed. He can, for a skinny guy, he can turn on that ball and hit the ball 110, 115 miles per hour leaving, you know. So we'll use these numbers, but the impact time, the ball comes in, boom, gone. That's short of a time. The question, two questions we'll ask. The first one, find the impulse. I. And two, find the force. Now let's see what happens. We know impulse equals what? We said impulse is the net force times the time. I don't know what the net force. But this is also equal what? To the change of linear momentum. So if I know these two, I can find the impulse. If I didn't know that, no big deal. I can find them using these two. We know what the mass of the baseball, 0.145. Final velocity, the ball is going to the right, that's 105. Well, I got to convert that, that's miles per hour, right? Yeah. So 105 divided by 2.24, roughly 47 meters per second. Coming in, the ball was coming at 98 miles per hour divided by 2.24, about 44. So I know the initial velocity and the final velocity. So the final velocity is 47. minus the mass, which is 0.145. What was the initial velocity? Negative 44. Because why? We're using right as positive, up as positive. Okay, so what do we have?
13.195.
Yep, 13.195. That's your impulse. We answered the first question. The second question, can we find what the net force is, the force between the bat and the ball? Well, the force times the time equals the change in momentum. This is what this one, this is the change in momentum. The force is unknown, I'm looking for it. The time is 0.04, and the change in momentum is 13.195. Can I get the net force? $330 Newton. 330 Newton. Learning about bats here. Let's see. That's it for now, I guess, on this. Now we're going to look into the subject, conservation of linear momentum.